Hello everybody. So now let us continue discussion into the next topic. Today we will be discussing about a very fascinating and exciting area which is termed as crystal engineering. And this area has been developed by Professor Gautam Radhakrishna Desiraju, who is currently a professor at the Department of Solid State and Structural Chemistry Unit, SSU, in ISC Bengaluru. Prior to this, he was in the Department of Chemistry at University of Hyderabad, where he developed this very interesting area of crystal engineering, and the idea was to extend the concepts of hydrogen bonding to understand formation of crystals. And the next very important contribution was whether we can utilize the understanding of hydrogen bonds between the different functional groups in the construction of the crystal structure, and this crystal structure will have different applications in terms of different physical and chemical properties. So this is what he termed as crystal engineering, that is the understanding of intermolecular interactions, for example hydrogen bonds, halogen bonds, pi-pi stacking, in the context of crystal packing, and then utilizing this knowledge in the prediction of crystal structures of different compounds. So first is the understanding of intermolecular interactions, for example hydrogen bonds, halogen bonds, in the context of crystal packing, which gives the desired crystal structure, the desired connectivity between the molecules to form solids having certain physical and chemical properties, and then utilizing this knowledge to predict unknown crystal structures of different kind of compounds. This exercise is referred to as the crystal structure prediction. So predicting a crystal structure is also very important, and the knowledge obtained from these intermolecular interactions can be utilized in the prediction of crystal structures. Now, before we go into the details of crystal engineering, let us have a comparison between molecular chemistry and crystal engineering. So in molecular chemistry, it is important to synthesize new molecules by mixing, say, A and B, or reacting A plus B to give new compounds C, where this process involves bond making and bond breaking, whereas in the case of crystal engineering, it is the synthesis of the crystal by the process of crystallization. So you have a compound, say A, which is say a solid at room temperature, and it is dissolved in a particular solvent. So in the then you allow it to crystallize. So n molecules of A can now crystallize to form the crystal. Okay, so you have a particular organic compound which you have prepared. The compound can be a solid, it can be a liquid at room temperature, okay, and you would like to now crystallize it. Obviously, a liquid compound will not give you a stable crystal, it will only be stable at low temperature. However, a compound can be dissolved in a particular solvent from where you can crystallize out the compound, and this is actually referred to as a supramolecular reaction. This is a supramolecular reaction. In this, there is no process of bond breaking and bond making involved, but what essentially is involved is the formation of hydrogen bonds between the molecular entities to give rise to this periodic arrangement of molecules, which we call as a crystal. So, when it comes to molecular chemistry, the individual atoms are very important. So, we talk about the atoms and the reactivity profiles of the atoms. But when it comes to crystal engineering, it is actually the entire molecule that participates in crystal formation. The entire molecule participates here. These are the specific atoms which undergo processes of bond making and bond breaking. In case of molecular chemistry, we are making and breaking covalent bonds primarily. But in case of crystal engineering, we are working with intermolecular non-covalent bonds. In the case of molecular chemistry, what is important to us as a whole is the reactivity profile of the molecule, and here it is the crystal. So, the net process in a molecular reaction is to form new molecules, and here it is to form crystals, new crystals. Here in molecular chemistry, there exists the concept of Synthon, such that you can actually have a target molecule and you can actually break down this target molecule into specific fragments using the idea of retrosynthetic approach or the disconnection approach, where the individual fragments have been obtained by a logical dissection or trisection of the bonds which are present in the final target molecule, and that is referred to as the process of disconnection approach or retrosynthetic analysis. Along the same directions, you have a crystal which is built up of hydrogen bonds because of the specific functionalities. So you can actually go back, and dissect these hydrogen bonds, such that because you know that these hydrogen bonds form because of the presence of certain functional groups. So it is possible to break down the crystal structure into the smaller fragments via an understanding derived from the hydrogen bonds present because of the different functional groups. And so the individual building blocks which are obtained are molecules. The final connection is the crystal structure, and in between we have these supramolecular synthons which connect by hydrogen bonds, eventually giving you the crystal. So the concept of supramolecular synthon becomes important. In case of molecules, the concept of structural isomers is very important, but in case of crystal engineering, the concept of polymorphism is very important, where you have a given crystal structure, a given molecule crystallizing in a particular crystal structure. However, under different conditions, you can get different crystal structures of the same molecule, resulting in the formation of polymorphs, and this phenomenon is referred to as polymorphism. We will discuss more about polymorphism in the later lectures. The next thing is, when we talk about reactivity, we talk about a transition state through which the reacting molecules have to go before they convert into the final product. Whereas in the case of crystal engineering, it is the process of nucleus formation, that is crystal nucleation and growth, that is most important. So the formation of the crystal is very important, and the crystallization can take place in kinetic conditions or thermodynamic conditions. Kinetic conditions are actually fast rapid conditions of crystallization and done at room temperature, and in the solvents which are highly polar and which have got the ability to evaporate very fast, and whereas the thermodynamic conditions involve doing crystallization at very low temperature, such that you maintain the thermodynamic equilibrium, and these involve solvents which do not evaporate very fast. So these kind of crystallizations take place over a period of many days to sometimes months. But what is critical in the formation of the final crystal is the formation of nuclei, and in the growth of this nuclei to give you the three-dimensional crystal structure or a three-dimensional crystal. And it is a chemical reaction which is very important in molecular chemistry, whereas in the case of crystal engineering, it is the crystallization process which is extremely important. So crystallization is a very important technique, and we do in the field of crystal engineering we do spend a lot of time in trying to crystallize molecules. Therefore, this becomes a supramolecular reaction compared to the traditional covalent bond making breaking reactions involving molecular compounds. So now we know that what is a crystal. The crystal is a periodic array of molecules that are held together by weak non-covalent interactions to produce matter of macroscopic dimensions. So ultimately we know that when we have crystals, the crystals can exist in different morphologies like plates, blocks, needles, etc. So we have, and inside the crystal we have this very periodic arrangement of molecules by this which are held together by these interactions to produce matter of macroscopic dimension. And there is an amazing level of precision because the arrangement of molecules is at very well defined precise location, and when a crystal forms it actually utilizes the symmetry operations of the space group to pack the molecules in the crystal. And when the process of crystallization takes place, it is the geometrical shape of the molecule, geometrical shape and size and the nature of different functional groups that participate in crystal formation. And so what we consider essentially is that the molecule as a node, a molecule is considered as a node, and then you have got a functional group, say Fg1 and Fg2, and now it is the interaction between this Fg2, we have the node molecule here Fg1, and then this process continues. And the recognition between Fg1 and Fg2 is by the hydrogen bonds or a different non-covalent interaction to give rise to zero-dimensional, one-dimensional or three-dimensional structures. And you can represent this particular molecule as a node, and the connections can be called the nodal connections which connect the different nodes. Let us for example take the molecule HCN, and it forms nice linear CHN hydrogen bonded, it forms a one-dimensional array, and this is a chain, this is a one-dimensional chain like structure. Now what crystal engineering says, if you were to have an acetylene group in a molecule and a cyano group, then these will interact with each other via the CHN hydrogen bond. These will interact with each other via the CHN hydrogen bond. So this CHN hydrogen bond will always be present in the crystal structure of an organic molecule containing the acetylenic linkage and the cyano functional group. So when you have this kind of specifics, and this recognition is always primarily observed in crystal structures. This operation, where we recognize different functional groups, constitutes what is called a supramolecular synthon. And the supramolecular synthon has been coined by Professor Desiraju, where he identifies these non-covalent building blocks and which are present in different crystal structures, and depending upon the type of functional groups, we can have different kind of supramolecular synthons which are present. And now if we consider another molecule, for example, which has the acetylic linkage as well as the cyano, then it will form so this kind of one-dimensional chain will be formed, again constituted of the highly acidic hydrogen with the nitrogen atoms of the cyano group forming CHN hydrogen bonds. So we see here again the supramolecular synthon is present in the crystal structure of another molecule. This is the 4-ethynyl 4-cyano biphenyl. 4-ethynyl 4-cyano phenyl. Okay, 4-ethynyl 4-cyano benzene. Okay, and you can now extend this to the biphenyl also. So if you have a biphenyl system, again if you have the cyano and the ethynyl group, this can continue further. So this is referred to as a supramolecular synthon. And along the same lines, we can now identify different kind of supramolecular synthons. Let us go to the next one. So we can have the classical acid synthon. So we have a carboxylic acid which is present in the molecule. Now traditionally, whenever you have a carboxylic group, it will form the zero-dimensional dimeric synthon. This is a very common observation, and therefore crystal structures of compounds containing the carboxylic group will have this synthon. But you can also have the non-dimeric where you form this kind of a chain. You can have a chain-like structure. Okay, so this forms a one-dimensional chain-like structure, but this is rare, but you can also have it present in some of the crystal structures. Similarly, when you have an imide functionality, this can also interact via these very specific NH-OC hydrogen bonds and these form dimers, cyclic dimers. And another key feature of this dimer is that these are centrosymmetric. That means there is a inversion point or a center of symmetry associated with this dimer, which relates the individual molecules. You can also have, instead of the dimer, you can now have a chain so you can have this one-dimensional chain consisting of NHO hydrogen bonds. So NHO hydrogen bonds can form dimer as well as chains, and it has been observed by looking at a large number of crystal structures that NHO chains are very common in comparison to the NHO dimers. And we can also now have other combinations. For example, say you have got an acid and you have got a functional group which contains a CN double bond along with the NH group. So it will form a OHN hydrogen bond and a NHO hydrogen bond. So this is very specific, because it essentially tells you that if you have a carboxylic acid along with a NH and a C double bond N, then it will form this kind of a dimeric motif, which is also called a supramolecular synthon. And you can also have it between so this is a cyclic dimer which is constituted from NHN hydrogen bond. So what it tells us is that if you have the specific functionality, then they will form these kind of NHN hydrogen bonds forming these dimeric aggregates. You can also have now, so these hydrogen bonds listed here are the strong hydrogen bonds, for example OHO, and then we have NHO hydrogen bonds, and these are NHN hydrogen bonds. And what was the most important contribution of Professor Desiraju was that he now wanted to extend the concept of supramolecular synthons to weaker interactions, particularly those involving the CHO hydrogen bonds and CHN hydrogen bonds in particular. So the concept was proposed that if you have got relatively acidic donors and strong acceptors, then CHO hydrogen bonds are also unique and they also exist, and in many cases in the absence of strong hydrogen bond donors and acceptors, it is the CHO hydrogen bonds and the CHN hydrogen bonds which play a very important role in the crystal packing. So let us look at some examples and where these kind of hydrogen bonds are present and constitute supramolecular synthons. So in this particular case, we can see that this is a alpha beta unsaturated system, and this particular hydrogen is acidic, and therefore it can participate in a CHO hydrogen bond. It is connected to an sp2 carbon, and hence it forms a CHO hydrogen bond, and this is a dimer, and this is also a centrosymmetric dimer because there is a center of inversion present here as well. And along the same lines, we can now have this kind of dimers as well, where you have got the alpha beta unsaturated group present, and this is the vinyl group, this is the CH2CH vinyl group present, and again this forms a CHO hydrogen bond. Now in this case again it was a vinyl group, but it was the alpha hydrogen which was involved, and here it is the beta hydrogen, which these are the beta hydrogens which are involved, these are the alpha hydrogens which are involved in the formation of these CHO dimeric units. And we can now extend the concept of hydrogen bonds to even larger sized supramolecular synthons. For example, we can look at this particular case. And now we have So you can now see the hydrogen bonding which exists here, NHO, NHN and NHO. So we can call this a donor of hydrogen, this is an acceptor, this is a donor, this is an acceptor, this is an acceptor, this is a donor. So this is very specific type of bonding. So whenever you have these kind of functional groups which are present, then they will form these kind of DAD, ADA kind of motifs, and this kind of specific information is actually coded in the system. So this kind of assembly process forming crystals have these kind of very specific hydrogen bonds which are present, and we can also now change this in the following way. So now we have NHO hydrogen bond, NHN hydrogen bond and NHO hydrogen bond. So here we can see that we have got donor, donor, and this is acceptor, this is acceptor, acceptor and donor. So we have a very different kind of arrangement here now. So we have got a different this kind of hydrogen bonding is there, and now we can extend this further, and we can now look at other cases. For example, we can also have so if you have a doubly bonded system, you have a CH and you have a cyno, then it forms CHN dimers, and we can extend this further. So now we can have this particular dimer does not have a center of inversion, whereas this one has got a center of inversion. So we have got two different type of dimers, and we can also now invoke halogen bonding. So if the hydrogen is replaced by a chlorine, so we can have CCl, Cl, we can have the Cl dot N halogen bonds, which can form these kind of structures. And we can extend this further now to include NH. So say you have got a NH donor and you have now got a nitro group present in your molecule, it will participate in the formation of this particular motif where this functions as a bifurcated donor. Okay, so now NH interacts with both the oxygen atoms of the nitro group, and it forms these kind of NHO hydrogen bonds where the oxygen comes from the nitro group. And you can also have, in place of NH, if you have iodine as a part of the organic molecule, then these can also interact with your oxygen atoms via iodine oxygen halogen bond to constitute the supramolecular synthon. We can have other examples as well, where you can have this kind of an arrangement where you have the acetone molecule interacting with a compound containing two NH functional groups, and here you can see that this is a bifurcated acceptor. So all these possibilities exist in case of formation of different kind of motifs, and we can also look at the phenyl ring, where we have already looked at the perpendicular motif. So you can have the parallel stacking, or you can also have the perpendicular stacking. Okay, so you can have the CH pi, or you can have the pi pi stacking, and these also constitutes synthons. So this became a very interesting subject now, because now we are able to identify the synthons. And now what is most important is we would like to see the history of supramolecular synthons. When did supramolecular, when did the history of crystal engineering, and this field of crystal engineering actually was started in 1960, okay, when organic chemist started doing solid state organic reactions. And this particular work was first pioneered by Smith, who was interested to perform dimerization reactions in solid state involving double bonds. So you wanted to look at the reactivity profiles of compounds which contain these double bonds. So the idea is that if you have a double bond and you have another double bond, and these can undergo dimerization to give you the cyclobutane ring, can we do a similar kind of processes involving double bonds in molecules in the solid state, such that these double bonds are actually pre-organized in the solid state, and they are within the reacting distance, such that when you shine light of a particular frequency, they undergo this stage of self-assembly, where they form the four-membered ring. So now in the next lecture, we will be looking at more fundamental aspects of crystal engineering, and how did this field start, and eventually culminated into a very exciting area of research. Thank you.